Um, why don't we go ahead and get started? So, we are thrilled to roll out the latest episode of the Quantum Seminar Series dedicated to the research and the academic quantum communities. The seminar is going to take place every Friday at noon Eastern Time, so right now, and it is hosted on the Qiskit YouTube channel. You may have noticed that I am not your typical host. I am not Zlatko. My name is Olivia. Zlatko couldn't be here live with us today, but I am very excited to be able to introduce today's speaker. So now it is my pleasure to introduce Professor Aditi Sen, who will be talking to us about the Quantum Communication Network. How are you today, Aditi?
Yeah, I'm fine. Thank you.
Great.
How are you?
I'm good. I'm excited about this. Okay, so I will introduce you and then we'll go ahead and get started. So Professor Sandé is a professor of quantum information and computation at the group at the Harish Chandra Research Institute. She received her Ph.D. at the University of Gdansk in Poland, then moved to Germany, became a Humboldt Research Fellow at Leibniz University, before she joined the ICFO, which is the Institute of Photonic Sciences in Barcelona, Spain. She was then briefly an assistant professor at the Jawaharlal Nehru University before she took on her professorship at Harish Chandra Institute. I also wanted to mention that the Council of Scientific and Industrial Research, which is the apex agency of the government of India for scientific research, awarded her the prestigious Shanti Swarup Bhatnagar Prize for Science and Technology for Physical Sciences in 2018, and she is the first female physicist to be given this honor. So Aditi, welcome. I'm really looking forward to this talk. We can go ahead and bring up these slides. And just as a reminder to everyone, feel free to ask questions or if you need any clarification throughout. I will be monitoring the chat and do my best to very politely interrupt Aditi whenever I see them. And then we can ask more questions at the end too if there's time. So we'll go ahead and get started.
Okay, thank you very much, Olivia. And thank you very much for a nice introduction and inviting me to this nice seminar series. I'm also very excited. So I will be talking about quantum communication network. And I am situated in Allahabad. Now it's called Prayagraj. So this is India, and I'm here and almost in the middle of India. And I'm from Harish Chandra Research Institute. This is actually the main building of Harish Chandra Research Institute. And I will be talking about, before going to the details, this work was done by this three of my PhD students. They were PhD students. Now all of them are postdocs in Europe. Amit was a postdoc, now is a faculty in India, and Ujjwal is also another faculty at Harish Chandra Research Institute. And currently, my group actually consists of these 5 PhD students: Shoptoshi, Srijan, Ratul, Ribhu, and Ganesh. And also, I will present some of the work which has been done by them, and also another postdoc, Dr. Shilari Tomal. So let's start. So I will talk about quantum technologies. Specifically, I will talk about quantum communication devices. Now, quantum communication devices can be broadly classified into 2 categories. One is classical information transmission via quantum state. Another is quantum state transfer. Now, when we talk about classical information transmission, that can be with security or without security. So this is more or less outline of my talk. First, I will talk about what is communication. And I will tell you that in these all quantum communication protocol, the basic ingredients that we require is entanglement. So I will give a brief introduction of entanglement, mainly the definitions I will present. Then I will present some of our work. So first I will talk about classical information transfer protocol via quantum states or in which involve several parties. So I call it quantum dense coding network. Then I will talk about some of our recent work, where we talk about sharing entanglement over large distance, which is a quantum network. And finally, I will talk about some secure communication protocol. So let's start. So what is communication? So I think in this COVID situations, we all realize the importance of communication devices that we use every day. From mobile phone, other phones, internet, and so on. Actually, if there is no internet, this talk would not have been possible. And we, by using this communication devices, we are able to connect with our friends, relatives, etc. In old times, we used to communicate each other probably by pigeons or by using animals. And I think not very long back, when I was kid, I used to have these kind of communication devices. And also I usually used to get informations by reading newspaper. Now probably all of us read e-newspaper. So this is a kind of evolution, you can think, of the communication devices from old time to the new time. Now, whenever we talk about communication, then at least communication protocol should involve at least two parties, which typically called Alice and Bob. And they are situated in two distant locations. So one can be, I'm calling here two names of the cities which are quite far apart. One is Allahabad, where I am situated, and this is Bangalore, which is in south. Just to tell you that they are in a far distant location. So of course they are not together like that, couple, so that they can communicate anyway. So typically Alice is the sender and Bob is a receiver. We can call in Indian name as well, Alia and Varun. They can be any two people, like the celebrities, like which are in the Bollywood movies or in the Hollywood, or the normal people like me. So Alice's aim is to send some information to Bob. Now, this information can be classical or quantum. What do you mean by classical? Classical means that Alice wants to send some bit to Bob, probably using quantum states. And another thing is sending quantum information. That means sending quantum state to Bob. And that means it can be qubit, for example. So Alice wants to send some arbitrary qubit to Bob. Now, any communication protocol should involve three stages. So one is sender, which encodes information. And as Lander said, that information is physical. And I also found that there is a Kiskit talk by Charles Bennett, where also he said about information is physical. So what do you mean by information is physical? Information must be encoded in a physical system as well as decoded from a physical system. Now, physical system means in a classical world, this can be in two colors of the ball, for example, red or green ball, sign of a charge of a particle, but these all states are orthogonal states. That means they are distinguishable. On the other hand, we know in a quantum world, informations can also be encoded in non-orthogonal states, because in a quantum world, we have orthogonal as well as non-orthogonal states, and they are indistinguishable states. So there is an encoding process that after encoding, sender should send this information to the receiver. Now this sending process can be either quantum channel or can be a classical channel. And finally, receiver will get the information, decode the message, and so what Alice has sent. So encoding, sending, and decoding are the three important steps in any communication protocol, as I will also elaborate when I talk about a particular communication protocol. Now, what the questions that I'm going to address in this talk is the following: that can quantum mechanics help to enhance the capability of sending information? So that means that when encoding, sending, or decoding, whether quantum mechanical postulates or properties help us or not. Now, before I go to the communication protocol, let us briefly introduce entanglement. So this is a nice review article on theory of entanglement by Horodeczkis. Now, I will define entanglement only for two parties. The similar way one can generalize this idea for multi-party scenario. So there are two parties, say Alice and Bob. They're again situated in two distant locations. And Alice prepares a quantum state phi A in her lab, and Bob prepares phi B in his lab. So the joint state is like that. Now, the states which Alice and Bob can prepare even when they are far apart, those states are called the unentangled states. Usually they are useless states from the perspective of quantum information processing. And examples, mathematically, it looks like that. And examples can be like this. So it's a 0, 0 or 1, 1. So here I have used spin degrees of freedom of quantum system. On the other hand, entangled states and typically useful states are those states that Alice and Bob are unable to prepare when they are situated in far apart location. Then how to share entangled states? So usually there is a source that prepare an entangled state, send one particle to Alice, another particle to Bob. Now, source can be also with Alice, so that Alice prepares an entangled state, keep one particle with her, and send another particle to Bob. Mathematically, entangled state cannot be written like that. And an example of an entangled state is a singlet state. Here, 0, 1 can be an eigenvector of sigma z, for example. Now, these definitions can also be extended for mixed states. So Alice and Bob can prepare those states or useless or separable states even when they are not together. So this can be written like that. Now, usually Alice and Bob will be able to prepare these states by using local operations and classical communication. And entangled states are those states which Alice and Bob will not be able to prepare when they are situated in far apart locations or when they use local operations and classical communication. An example can be a mixture of singlet and say 0, 0. Now, here I want to stress that although the entanglement theory has been developed in last 30 years or so, but still we don't know that given a state rho AB, it is not easy to detect entangled state in arbitrary dimension. Now, there are also, we have written a chapter of a book in where we talk about only theory of entanglement. Now, there are also other kind of quantum correlation exists in nature. And if you're interested about knowing about other quantum correlations, you can look at these 2 review articles. One of them, the second one was written by us recently. Now I talk about
Aditi,
the
before we move on quickly, we actually already have one question, so I'll just interrupt you really quick. So someone from the chat wanted to know, I think something that was related to your previous slide, and they asked, is any type of quantum information processing possible without using entanglement?
Yeah, actually that's a good question. It's true that up to a certain point, people believe that all the quantum information processing tasks, I mean, okay, we even don't know whether all the quantum computations algorithm where we really need entanglement or not. It's not proven. But if we talk about quantum communication protocol, most of the protocols we require entanglement.
Right.
But it's also shown recently that this other type of quantum correlations like quantum discord, etc., they can also be useful for certain information processing tasks. It was also shown. So if he or she is interested, he can look at this articles, this review article.
Okay, perfect, great. I'll mute myself again.
So I continue. Okay, so now I will talk about classical information transmission via quantum states. So specifically, I talk about quantum dense coding protocol. So suppose Alice wants to send the weather information to Bob. Now here I choose a city, Kolkata, in India. So suppose Alice wants to send the weather information from Kolkata. So there are few possibilities. So for example, it can be sunny, it can be windy, it can be raining. Okay, in Kolkata it is not possible for snowing, but suppose there is a city where snowing is also possible. So there are 4 options. That means there are 2 bits of classical information that Alice wants to send to Bob. Now, classically, what Alice can do, as I said, that to encode any informations, we require physical system. So here, suppose Alice uses the balls, the different colors of the balls. So, for example, if it is sunny, Alice will send a blue ball. If it is snowing, it's yellow, and so on. So what Alice can do, depending on the weather situation, Alice will send this ball via, say, in a box, and then that box can be sent to Bob. And Bob can decode this message because Bob can distinguish them from the color. So you see that to send these 2 bits of classical information, Alice needs 4 colors of ball. So that means Alice needs 4 distinguishable objects. In other words, Alice needs 4 dimensions. Now, even in classical world, instead of balls, you can use different, for example, different waves, different objects, but the protocol remains same. So to send 2 bits of classical information, Alice requires 4-dimensional system. Now the question is whether quantum mechanics help. Now this was solved in 1992 by Bennett and Weissner, and they said that indeed it is helpful if Alice and Bob a priori share a singlet state. Now how? Now Alice, depending on the message, Alice performs one of the unitary operator on her particle. This is the encoding process. And by performing this unitary operator, Alice actually can change the shared state to one of these 4 states. Now, after encoding, Alice sends her particle to Bob via noiseless channel. And so Bob, after sending, Bob gets one of the 4 states, which are singlet and triplets. This is the sending part. Now Bob has to decode. Now, since they are orthogonal, Bob can always find a measurement by which Bob can distinguish them. So Bob can decode the message. So if Bob gets psi minus, Bob is sure that it's sunny at Alice's place. In psi plus, Bob knows that Alice's place is snowing today, and so on. So Bob can decode the message. But here note that to send these 2 bits of classical information, Alice only needs 2 dimensions for encoding. So encoding is done only at Alice's part by performing these unitary operators. So Alice only uses 2 dimensions. So as you see that what we get from this message, classically Alice requires 4 dimensions, while for in quantum case, Alice requires 2 dimensions. So provided Alice and Bob a priori share an entangled state, in particular singlet state. So we win. Now this also has been demonstrated experimentally by using polarization photons, by using polarization degrees of freedom in 1996. And there are many other experimental experiments has been done to implement or to realize tails coding protocol. Now, up to now, I have discussed when Alice and Bob share an singlet or the entangled states. Now, in a realistic scenario, it's not possible to share a perfect singlet state. It will be in general a mixed state, arbitrary density matrix. Then how will we find that what is the dense coding capacity, or how much, whether we really get some advantage over classical protocol or not? And this was addressed in these papers. So as I said, here the Alice's task is to send some classical information, say I, just like previously, that was the weather of the city. So there was 4 options. Here I am denoting that by I, and which occurs with probability pi. So as I have said, all the options may not occur uniformly, because it can happen that snowing never happens in Kolkata. So the probability is 0 in that scenario. Now, depending on the message I, Alice performs unitary operator Uy on her part and creates this ensemble, that is Pi rho I AD. Then, so as I said that in case of singlet, these rho i's are the singlet and triplets. Now, Alice sends her part to Bob via quantum, this noiseless quantum channel. Bob's get the state. Now, since now they are not pure state, so they may not be orthogonal in general. So this ensemble, Bob's task is to gather as much information as possible about I from this ensemble. Now, how will Bob gather information? Bob, of course, perform measurement. So we define some quantity which is called accessible information. So this is defined as a maximal classical information that Bob wants to extract from the ensemble this. Now, of course, you have to optimize here over all the measurement strategies, and this is very hard. In general, it's not easy to perform. So you use an upper bound called Holevo bound, which is defined like that, where rho bar is the average state that Alice produced or Alice and Bob have, and S is the von Neumann entropy defined like that. Now, it was shown that the Holevo bound can be achieved asymptotically. And so, capacity of dense coding is exactly equal to Holevo quantity, where we have to perform maximization over only encoding. So decoding part is simplified due to the Holevo bound. So we have to maximize over unitary, perform the Alice, and the probability in which Alice perform the unitary.
Before we move on too far, Aditi, I have 2 more questions for you. So someone from the chat would like to know, does the decoding protocol need to be shared beforehand before the information is sent?
Yeah, actually the entire protocol has to be before is fixed in a sense, because even in the classical case, if Alice and Bob previously haven't fixed that which ball they will send for what message, then the Bob of course cannot decode it. Similarly here, it is known that they share a singlet state. It is also previously settled that when it is sunny, Alice applies identity, or in other cases when it's snowing, apply sigma z and so on. So it's prefixed so that at the end of the protocol, when Bob measures and gets one of the states, for example, in my slide, sorry. Yes. So in my slide, as you see that you have a, so if Bob gets 5 minus, immediately Bob can infer that it is windy at Alice's place. So this entire thing that whenever this is sunny, it is identity snowing sigma z, and windy it is sigma x, and raining it is sigma y, is already prefixed so that Bob knows this.
Yes. Okay, makes sense. And then another question was, what is meant by this noiseless channel? Is it truly noiseless in real life, and would it be vulnerable to any eavesdroppers?
No, here there is no question of security because we are talking about only insecure channel. Now the noiseless channel means whatever Alice after encoding, if Alice wants to send singlet and triplet, Bob should get exactly this states. So Bob should not get, instead of singlet, Bob should not get a noisy singlet state. That is what I mean by noiseless channel. I will also talk about a noisy channel in later part of my talk.
Okay, great. We'll come back to that later then. All right, yes. I'll mute myself again. We'll keep going.
So yes, and this capacity can be found exactly. And here, dA is the dimension of the Alice's subsystem, rho b is the Bob subsystem, and rho ab is shared by Alice and Bob. Now, as S is the von Neumann entropy, here you note that if Alice and Bob a priori doesn't share any entangled state, then the classical protocol only gives us log of dA bits. On the other hand, if they share an entangled state, or if they shared some quantum mechanical state previously, I mean beforehand, then if this part is non-zero, then this is good, or this is advantageous for dense coding. So we can tell the state, quantum state is said to be advantageous for dense coding. That means we get quantum advantage when this part is non-zero, that is greater than positive. Now for pure state, S of rho ab is 0, And so it just goes to this. So log dA plus S rho B. Now here note that S rho B is also an entanglement measure for PO state. And so whenever a PO state is entangled, it is dense codable, which is not true for arbitrary density matrix, that is for mixed state. Now, as I said, that sender and receivers share a quantum channel a priori, which can be a mixed state or pure state. After encoding, sender sends the state or quantum state to the receiver. Now, while sending, that channel can be noiseless as well as noisy. So the noiseless scenario was solved in the previous paper that I have shown you, and noisy scenario was partially solved in this paper. And why partially? Because they solve only for a covariant channel, because for an arbitrary noisy channel is hard to solve. So what is covariant channel? A channel lambda C is said to be a covariant channel if one can find a complete set of orthogonal unitary operators Wi acting on the state rho such that this condition is satisfied. For these channels, for these lambda C, this problem is solved. That is, after sender's encoding, if Alice sends the encoded state via noisy channel, that means via covariant noisy channel, then we know also the capacity. Now, when we talk about the information transmission between single sender and single receiver, this has a very limited commercial use. So we dream to set up, or we dream to have a communication channel where we have several senders and several receivers. Now, we can think of a scenario, for example, a newspaper office, where the reporters are situated in distant locations, and reporters are sending information to the newspaper editors who actually finally edit the news. And so this is the scenario where the several senders wants to send messages to their particular editor for certain news to cover. Now, this is the scenario. So where there are several senders and we have, say, one or two receivers, they a priori share a quantum state. And then after encoding, sender sends their part to the receivers via noiseless or noisy channel. Now, why I restrict myself to two receivers, it will be clear in a few minutes. So let's concentrate on only one receiver and also the noiseless channel. So this is a scenario. So you have several senders and a single receiver, and they share a quantum state this. So this is an n+1 party quantum state. Alice encodes, and this Alice, Charu, and so on, they encodes their informations on her part and sends all their parts to a single receiver, Bob. Now, as there is only a single receiver, you understand that the decoding part is still simplified because we can again maximize over only the Holevo quantity. Because Holevo bound is a bound on the accessible information, which is by global measurement. Since all the senders sends their part to the receiver, so Bob can apply global measurements for decoding, and so we can apply the Holevo quantity. So this optimization was also done in our paper in 2004, and we have exactly found the capacity of dense coding. Now, again, for a noisy scenario, after encoding, when the noisy channels are used, also it is partially known only for this covariant channel, and that was solved by the Dagmar Bruce and her group, as I have already mentioned the reference before. Now, what about two receivers? Now, that means here there are several arbitrary number of senders and there are two receivers. And they all, this n+2 party, share a quantum state. Now, their receivers are also situated in two distant locations so that they are also not, for decoding, they cannot apply global measurements. So they have to apply local operations and classical communication. Now, in this scenario, whether we can we can find the capacity. And it is indeed possible to find, because this capacity of dense coding can be shown to be upper bounded by the Holevo quantity, which is known as local Holevo bound, which we found in our paper by Piotr Badjian, Miha Horodetsky, Ujjwal, and myself. And then this Holevo quantity now has to optimize over the encoding. Just like before, we have optimized the Holevo quantity. Now you can tell there previously it was exactly equal. Now why is it only upper bound? Because in this local Holevo case, we don't know whether this can be achieved asymptotically or not. And so we only get an upper bound. And this maximization over these unitaries is again possible, and this was done in this paper, and we found the upper bound on dense coding capacity for n senders and 2 receivers. Again, if after encoding, if we use noisy channel, specifically if we use covariant channel, also this upper bound was found in a recent paper with one of my student Tomunno, and we found an upper bound on noisy dense coding capacity. So the situation is the following, that when you have n senders and 2 receivers, both noiseless and noisy scenarios, we found the upper bound. Now, when you have more than 2 receivers, this dense coding capacity is still unknown, because when you have more than 2 receivers, we don't know the local Holevo type bound. The local Holevo bound that we found with Piotr Badjian, Miha Horodetsky, and Ujjwal, this bound is only applicable when there are only 2 parties involved. If we have more than 2 parties, the Holevo-like quantity is not known. And so it's still not possible to find dense coding capacity in this network. And as you know, that LOCC doesn't have a good mathematical form. And so it's not so easy to find also the local Holevo type quantity for arbitrary, when there are arbitrary number of people involved. And actually we are also trying, but we still are not able to get that. There are another kind of network that we can consider, for example. Suppose there is only a single sender, but many receivers. But now senders and receivers share an entangled state. But senders now wants to send individually certain classical message to all the receivers. So this is a different scenario than the protocol that I have described before. But in this scenario, we have recently found that if we want to do a dense coding protocol in this scenario, so one can show that senders can only get quantum advantage with a single receiver. So if S1 and R1 get the quantum advantage, then S1 and R2 cannot get quantum advantage, or S1 and R3 and so on, they cannot get quantum advantage. So that's why we call it exclusion principle of dense coding. Now I move to another dense coding protocol. So as I have told you, the dense coding protocol involve 3 stages, like encoding, which we have done by unitary operator. Then there is a sending via quantum channel. That channel can be noiseless as well as noisy. Then there is a decoding part, which we use, for example, the Holevo or the local Holevo quantity. But both this decoding part is probabilistic, because we have an arbitrary mixed state or arbitrary pure state, and then we perform measurement, and we cannot gather information. So we want to only get that how much Bob can get, or we optimize over or we maximize over the access or the mutual information, or the which we call accessible information. So decoding was asymptotic and probabilistic. But suppose I consider decoding to be a singles route. That means instead of maximizing probabilistically, we want to create deterministically orthogonal states. And this was introduced by Oppenheim, Resnick, and Moses in 2005. So the scenario is the following. So suppose again Alice and Bob share an entangled state or any arbitrary pure state, the psi. Alice again performs unitary operator depending on the classical information that she wants to send to Bob, that is I. Now here the aim is that Alice has to design the protocol in such a way that after encoding, when Alice sends her part to Bob, Bob only get orthogonal states. That means we have to find over the encoding strategy so that maximum number of orthogonal states are produced at Bob's end. So this is actually mathematically we have to find out that after unitary operator on Alice's side, the state that we get, the resulting state with the initial state has the inner product to be 0. Now, we can tell that a state is said to be deterministically dense codable if the maximum number of orthogonal unitary operator n max is greater than d, because this is the classical limit. Now, it was shown in this paper that deterministic dense coding is not possible for 2 qubits, although it is possible for 2 qubits. So if you have a 2 qubit set like this, then deterministic dense coding is possible. We know that the entanglement and dense coding capacity in a previous scenario that I have described for pure state, it is related with entanglement, as I have told you, because for pure state, this term is 0, and so this only survives, and this term is exactly equal to entanglement content of the pure state. However, if we talk about a deterministic dense coding, it was shown that entanglement and deterministic dense coding is not related, because nmax of psi1 can be greater than nmax of psi2, although entanglement follows an opposite hierarchy. Moreover, it was shown that in d cross d state, if you have for a d cross d state, we cannot have nmax psi d square minus 1. As you know, the maximum is d square, and if we get nmax to be more than d, then of course it is quantum. But somehow there is some no-go theorem which tells us that nmax psi cannot be d square minus 1. Now we, in our recent work, we actually extend this deterministic dense coding protocol in a network. That means we have 2 senders and a single receiver. For example, it can be many senders and single receiver. Now the question that we can ask, just like no-go theorem in 2 qubits, do we have a similar no-go theorem for 3 qubits? That means with qubit, but it's for only 2 qubits. That is, 2 qubit has some specialty. We know that in case of 3 qubits, there are 2 kinds of states which are interesting, which is GHZ class and W class state. Whether deterministic dense coding, if we somehow want to characterize these 2 class of states, whether we get any difference. Now, first theorem that we prove is the following, that deterministic dense coding is not possible for 3 qubit generalized GHZ state, except the point where it is a GHZ state. So this is the form of the generalized GHZ state. Alpha equal to 1 by 2 gives us the GHZ state, Greenberger-Horn-Zeilinger state. We show that deterministic dense coding is not possible for any alpha other than 1 by 2. And the proof goes that we show that it is not possible to have more than 4 orthogonal unitaries, because here the nmax psi should be 4 for classical case, and for quantum case, nmax psi should be more than 4. We have also shown that deterministic dense coding network is not possible by 4 qubit generalized GHZ states. So we are also conjecture that it is not possible for n qubit generalized GHZ state, but we are unable to prove that. But our proof in 3 qubit and 4 qubit hinted us that it is not possible for n qubit as well. Interestingly, this is not only the property of qubits, because we found that if we have a W state, that is generalized W state, then there is a region. So this is the alpha and beta, the parameters of the W state. And we show that in this region, this is like apple right region, here the deterministic dense coding is possible, which gives us advantage, or that gives us quantum advantage. So as you see that 4 is the classical bound, which is this violet color, and all the other green, orange, red are all the states which are more than 4. And so in this case, in this scenario, if for these states, by using these states, we can have a deterministic dense coding and we get quantum advantage. Now, this is an interesting observation, because usually we know most of the communication protocol, generalized GHZ state gives us advantage. But here we find that generalized GHZ state doesn't give us advantage, although generalized W state can give advantage. This also clearly shows that deterministic dense coding has no relation, or has no direct relation with entanglement. Now we also
So
have
Aditi,
yes.
just for clarification for maybe some of our audience members who aren't as familiar, can you talk a little bit about what these states actually are, the GHZ and the W states?
Yes. So this is the state that I have written. This is the generalized W state. Okay. So you can think these zeros and ones are the qubits, right? So you think that 2 up spin up particle and 1 down. Okay. And you take a superposition, then this is the generalized W. And when the alpha beta are all equal, that is, it is 1/3, then this is the W state. And for other alpha beta value is called generalized W. Similarly, generalized GHZ state, as I said, that any other alpha value give you generalized GHZ state. So it's all up and all down state. And this is, as I said, this G for Greenberger, H for Horn, and Z for Anton Zeilinger. So they have used this state to show other things, but people usually call these states as GHZ state. And this is generalized because alpha equal to 1/2 give me GHZ state, and other alpha values give me generalized GHZ state. Is it clear?
Yes, I think so. Okay, great.
So if we have a GHZ class W class state, which is different than generalized GHZ and generalized W, I haven't given the definition, but these are the 2 different classes of states. And it is known that if you consider a state from the GHZ class, you cannot go to a W class by local operations and classical communications, deterministically, even probabilistically. So it is not possible to convert any state from this state to a W class state. And so it is interesting because they are 2 distinct subsets of a 3 qubit state. Now, numerically, what we find that although generalized GHZ states are not capable for deterministic dense coding, but generalized W states can give us deterministic dense coding protocol, or can give quantum advantage. And in case of GHZ class and W class, we get that these number of states can give us quantum advantage. And note that here GHZ class actually performs better than the W class state. So we have actually solved this problem for multiple sender and a single receiver. This one-shot dense coding capacity, deterministic, and as well as conclusive, which I am not going to discuss. If you are interested, you can look at this paper in which was published in 2019. Now I move to the sharing entanglement over large distance. So as we know that the quantum state transfer, that is quantum teleportation, is an important protocol where the task is to send an arbitrary quantum state from Alice to Bob. And classically, we know that to send an arbitrary quantum state, we require infinite amount of classical communication. Now, if Alice and Bob a priori share an entangled state, then 2 bits of classical communication is enough to send an arbitrary qubit. And this was introduced by the 6 people in 1993. Now, we also know that this is not only theory, but there are a lot of experimental progress. For example, by using photons, by polarization degrees of freedom. Recently, it was shown that there can be a shared entanglement possible between 2 cities in China, which are 1,200 kilometers away. And this was led by Professor Pan. And so just reality that there are 2 cities in India which are almost 1,200 kilometers away, which is Ahmedabad and Hyderabad. And now it's possible to perform teleportations in this distance. It's also possible to perform teleportations by using ions. And recently it was also shown that by using matter qubits, also one can perform teleportation. It was nicely written that it was discovered that trapping the atoms in optical cavities can overcome some of the previous obstacles facing matter teleportation, and they are able to perform teleportation across a record-breaking distance of 21 meters. Already in their paper, or people have said that this improvement actually could open the door to realize quantum networks with many nodes for teleporting qubits to various destinations. And this is exactly the questions that we want to address. So just like a communication network, here I actually put flight details of Air India in India. So, so our idea is to share entanglement over large distance. Now, there was a long back protocol in 1998, which is known as quantum repeater. So suppose sender wants to send a quantum state or share quantum state, entangled state to the receiver, whose distance is quite big. So as we know, when the distance increases, this decoherence increases, and entanglement, or the keeping state entangled, is hard. So what is the remedy? That they showed that if sender or the entire quantum channel can be divided into small parts, like there are different nodes in between, and then these nodes perform certain measurement, then finally, after measurement, sender can share an entangled state with the receiver. For example, one can check that if all of them are maximally entangled state, then after Bell measurements in each node, sender and receiver can share a maximally entangled state. Now, in general, as we have already talked about, that this sender and receiver or these small sectors will not be a maximally entangled state, because that's an ideal situation. In general, it will be a non-maximally entangled state or mixed state or noisy entangled state. Now, the question is, what is the critical noise that is allowed so that finally sender and receiver share an entangled state which they use for communication purpose. Now, initial protocol of quantum repeater actually said that sender and receivers, these nodes, actually share many copies of the state so that they perform distillation. So they distill this noisy entangled state to a highly entangled state or maximally entangled state. And then they perform measurements so that finally sender and receiver share an maximally entangled state. But in this paper, we modify a bit. We said, okay, there is only a single copy share, and then whether we can find out that what will be the threshold noise that is allowed between this initial state, and after measuring, say, for example, Bell measurement, sender can share a entangled state with receiver, which can be useful for any quantum information processing task. Now, we mainly demonstrate it with a Warner state, which is a singlet state with a noise identity operator. P is the noise value. So this is the parameter. Now we know that the oneness state has very rich or nice properties. So we know that when P is less equal to 1/3, it is separable. So 1/3 to 1, it is entangled. Moreover, it violates Bell inequality when P is greater than 1 by root 2. So it shows that there is a region where the state is entangled but doesn't show, say, Clauser-Hahn-Shimony-Hall Bell inequality. There is in a Warner original paper, he has shown that up to P equal to half, one can construct local hidden variable model by projective measurement and so on. I'm not going into detail of that. But what we have shown is, suppose there are n Warner states shared between these parties, and there is prefix nodes which I have shown here by yellow. That nodes we want to share entanglement. Now, what is the way to share entanglements between these yellow nodes? What we said that the first we perform a measurement, which is a global measurement in these n parties, and we perform local measurement in green nodes, so that after the protocol, yellow nodes share an entangled state. So this is our building block to share entanglement in prefix node. Now, with this building block, now we go to a one-dimensional quantum network or the lattice. As you see, there are 4 yellow nodes. So 1, 2, 3, 4 want to share some entangled state. So they perform, these are called the nodes. So the blue ones are the nodes. And this blue one, you can see that in this node, there are 4 states which are coming in. And this is called the coordination number. So in this lattice, the coordination number is 4. So in this blue nodes, they perform global measurement. And in this red nodes, they perform local measurements, so that at the end of the protocol, 1, 2, 3, 4 can share entanglement. Now, in this network, when we talk about multipartite states, it's very hard to detect entanglement. So we use Bell inequality to detect this entanglement. We show that in this one-dimensional network, if we fix coordination number to 4, here in this picture, you see the coordination number 4 because there's 4 red dots in one node. And so it is a coordination number 4. So if we fix coordination number to 4, then if we increase number of nodes, then we need actually more and more entangled state to violate Bell inequality in between 1, 2, 3, and 4. So we need less noisy state to start with, so that at the end, we 1, 2, 3, 4 share a entangled state. On the other hand, if we fix the nodes to be 5, then with the increasing of the coordination number, we see that the critical threshold noise decreases if the final state is multi-party entangled or the resulting state violates multi-site Bell inequality. We then apply the similar concept to two-dimensional quantum network like square lattice, where the coordination number is 4 again. And in these red nodes, for example, we want to share entangled state. So we give an explicit proposal that how to share entanglement between these 4 sites. Or in this triangular lattice, we also show how to share entangled states between, say, for example, multi-site entangled states between these yellow nodes. Now, we have these, each party or each these lines actually refers to a noisy entangled state, for example, Warner state. We find that if really A, B, C, and D wants to share an entangled state, what is the critical value of noise required to the initial state so that they finally get a non-local correlation? We also answer some fundamental questions. For example, we find that if the initial states are non-CHSH, that is non-Bell inequality violating, then still the final states can violate Bell inequality, violate multipartite Bell inequality, and to obtain this kind of super additivity, we require minimum coordination number to be 6. That is, we require the triangular lattice. Now I come to the last part of my talk. So I now talk about up to now, whatever protocol I have described, all this protocol doesn't involve security. So there is no question of security. So there is no third party who trying to gather information which is flowing from Alice to Bob. So what is secure communication? Now, quantum information is inherently secure. So we only talk about classical information transfer security. So there is Alice and Bob who wants to send some information to, Alice wants to send some information to Bob. And there is a third party, which we call eavesdropper. Eavesdroppers aims to gather as much information as possible that Alice is sending to Bob. And we know that this secure communication is extremely useful in nowadays, from internet banking to internet marketing, in national security, and so on. And the quantum classical cryptography system that nowadays we use are all secure, and they are based on the fact that some mathematical problem cannot be solved in our computer. However, these problems can be solved by a quantum computer, and so we require quantum cryptography. And quantum cryptography security is based on the validity of quantum mechanics, and it is secure even when quantum computer exists. And the initial two protocols, the famous one is the Bennett-Brassard 1984 protocol and the Arthur Eckert 1991 protocol. We also know that in quantum mechanics, if one wants to disturb quantum states, it can be detected. So this property will be extremely useful for detecting eavesdropper. But this is what we are talking about, the ideal situation. So we have a threshold to be achieved. So this is the Bennett-Brassard and Eckert they're talking in some conference. And this is a picture actually taken at Harishchandra Research Institute when Charlie was visited us and was taking a picture of us, and when some of our students has taken his picture. So recently we proved a complementarity relations which provides a bound on the secret key rate on a quantum key distribution protocol. So in particular, we show that purity between Alice and Bob and the mutual information, quantum mutual informations between Alice, Bob, and eavesdropper, or C, is following certain complementary relation. Now, purity we quantified by the von Neumann entropy, and we somehow make it to make it dimensionless. We actually divide this, and this is the definition of quantum mutual information. S is the von Neumann entropy. Now, this complementary relation then can be used to obtain an optimal key rate. Now, when we talk about individual attack and when we talk about just one-way communication, then we know that optimal key rate can be obtained by via Sitzer-Corner criteria. And the Sitzer-Corner criteria actually tell us the gap between the mutual informations of Alice Bob and Alice Eve or Bob Eve pair. So by using this complementary relations, we are able to get a bound on secret key rate, where Hg is the Shannon entropy of the error rate, and S is the von Neumann entropy, and rho AB is a shared initial state. Now, we also have worked extensively on monogamy of quantum correlation measure. As monogamy said, that as we know in the society. So here also, if Alice and Bob is maximally entangled, then we are sure that Alice and Bob cannot be entangled with the eavesdropper or the third party. And this is an ideal situation again. In general, if Alice and Bob is, say, less or non-maximally entangled, then there can be a possibility of sharing entanglement between Alice and Eve. So Eve can gather some information that Alice and Bob are using to Alice and Bob using to share some information. Now, this trade-off relation was first quantified by this in this paper by Kaufman-Kundrutis, where Q is any quantum correlation measure. And in this paper, they show that if Q is concurrence square, then this satisfies this monogamy relation. And later on, it was proven that if it is negativity squared, then it also satisfies monogamy relation. But if you have quantum discord as a quantum correlation measure, so if Q is, say, discord, then discord doesn't satisfy the monogamy relation. Now, this also can have some implication in quantum cryptography or the secret key rate. Now, this I'm not going to discuss because I'm running out of time. So if you are interested, you can look at the chapter of a book written by some of us. And here we discuss about monogamy of quantum correlation. Finally, I will talk about some of our recent results on no masking theorem. So what is masking? So if quantum information is hidden from subsystems and spread over quantum correlation, then we call masking, it is masking of quantum information. Now, if quantum, that means this quantum information is replaced by classical information, then if this classical informations can be hidden from subsystem and can be spread over quantum correlation. That means masking of classical information is possible. Now, mathematically, the masking of quantum information is as follows. Suppose an operation S is set to mask quantum information contained in some state, say AK. Then we map this state to a higher number of parties, say psi k, such that all local density matrices are identical. That means this rho A and rho B are identical, so that they do not contain any information about the value of k, which we use to mask the information. Now, what we have shown that it is not possible to mask arbitrary quantum states. And we show that this has implication or applications on secret sharing protocols, that is quantum cryptography protocol involving several senders and receivers, and also into no qubit commitment. I'm not talking about secret sharing, but just to introduce the no qubit commitment. Now, no qubit commitment is same as no bit commitment. So here the task is the following. Suppose Alice commits a qubit from a certain state set to Bob. So later Alice unveils to Bob that she has indeed committed to that qubit. Suppose Alice wants to commit to an arbitrary state of a qubit from a set, say psi. What she can do, she prepares an entangled state, say psi AB, for each this set state from a set, with the condition that the local density matrices are independent of this psi. As I have told you, this is not possible because this is the no masking theorem. So no masking theorem tells us that no qubit commitment is possible in a quantum world. So I come to the end of my talk. I think I am on time, Olivia. So I talked about future technologies, mainly quantum communication network or quantum internet. This communication network can be with or without security. Now, this is a group, most of the works that I have presented is performed in this group. And this is a quantum information and computation group at Harishchandra Research Institute. Here, some members have left because they went to faculty position, joined, or in the as a postdoc. But currently, we have 15 PhD students, 5 postdocs, and 3 faculty members. And thank you very much for your attention. I'm really happy to be part of this program. Thank you.
Thank you so much, Aditi. That was so thorough, and I learned a lot. I think we have a couple questions that we didn't get to, sort of conceptual base, but let me go back and find them in the chat. Oh yeah, so one question that kept coming up is when you were modeling noise for some of your experiments in your more theoretical papers, how did you do that?
Yeah, actually, I'm a theoretician, so I think you are experimentalist. You probably will not agree. Uh, so the noise model is actually we somehow considered that this is a CPTP map that is completely positive phase preserving map, and so these are the operator form, and
Okay.
we use that. And of course, as I said, that for arbitrary CPTP map, it is very hard to prove any capacity or anything in general. So we use certain properties of that map to prove things. So as I have shown you in case of James coding, that there are maps like covariant map, which has certain property which we can use. Very other, we can also use particular channels like depolarizing channel, which actually with certain probability it doesn't disturb the state, and with certain probability flips the state, like it applies sigma x, sigma y, sigma z. There can be a phase flip channel which actually changes the phases. Uh, Also, there can be an amplitude damping channel where the channel has a kind of damped the amplitude, and this can be probably experimentally. It's also possible to consider. When we also, I think I haven't at all discussed when you, we also have done some work where we talk about communication network, where we use continuous variable system or we use photons. Then there is also dark count and other noisy thing which we also consider.
Mm-hmm. Okay. Yeah, that makes sense to me. Okay, and then one more conceptual based question. A lot of people were asking, what exactly is a quantum channel?
Yeah, so that's already, as I said, that this is a kind of map which actually map, it's a mathematically it's a completely positive phase preserving map. So it's a positive apparatus which actually complete positivity means that if you have a say a lambda or it acts on rho, then it is positive. And on top of that, if it acts on rho and its extension, then also it keeps positivity. That is called complete positivity. And so if, and of course, it preserves trace and hermeticity. And so if we consider that map and we apply to the state, then it goes to some rho prime. And we talk about that property of rho prime. Of course, we can consider a specific channel and address the questions, and we may gather more information. That's true.
Okay, cool. All right. Well, I think those were all the questions we had. If anything was unclear, I think Aditi linked to a lot of good sources and papers, some of which I'm already familiar with, and I know they're really good sources, so I would recommend definitely looking those up. So at this point, I just want to thank you again for coming to our seminar series. I think this was a
Thank
great
you.
talk, really educational. Thanks everyone for tuning in and for asking questions. We have these every week, like I said. So if you want to make sure you don't miss any of these in the future, just press the subscribe button. And yeah, all right. Thank you so much. Hope you have a good rest of your day, everyone.
Thank you.